All right, here we go. Got the online folks in. 4 o'clock. Got a fresh new meme for you. You're welcome. Welcome back to your least favorite class. I mean, your favorite class. I can never remember. If you're only taking one class, it's simultaneously your least and most favorite. So there you go. Maybe that's how you want to go about it. Announcements. Homework number 5 due on Thursday. Okay. So I've had some questions on it. Good questions. So keep at it. I'll be office hours tomorrow, 8 a.m., 9:30 a.m., just like every single day. And that's that. So I thought today, since we've kind of been hitting the math a little bit hard, we might start off with a somewhat practical example so that we can sort of get grounded in some of the stuff that we're doing right now by talking about some more practical information. So I uploaded to Blackboard a practice problem that we're going to do right now. And I will post that here for everybody to see. And if you want to follow along on Blackboard, you can also do that. So let me get that here and here. All right. So we'll start with a practical example, and this is going to have to do with plane stress, transformation of stresses, bringing back some of the things that you love and or hate from ME3005. And so we'll just make sure that we're all kind of completely locked in and dialed in here so we can sort of just see some practical applications maybe of what we're doing. So here we've got a thin unidirectional carbon fiber epoxy tube. And it's under some torsion and also some internal pressure. Complicated, right? So we want to determine what is the stress state on the surface of the material in principal coordinates, given that the shaft have these certain geometric parameters, and that the unidirectional sort of orientation of the fibers with respect to the longitudinal axis of this particular shaft is sort of 45 degrees. So hopefully we're all kind of following that idea. So I'll give you guys a second to sort of copy this, and then we can work through it. We've been doing a lot of math and stuff, so I wanted to bring it back to some sort of practical engineering problem, etc. What manufacturing process was likely used to make this tube? What did you say? Totally RTM. Incorrect. Who's got it? Filament winding. The right one. Riley says pultrusion. Could also be pultrusion. So with this 45-degree orientation, highly unlikely. So what you're going to put on your exam too, Alex? The right one. No, it was the left one. Left Twix or right Twix? I have seen Arrested Development. Not all episodes, but many episodes. I don't know about that one off the top of the head. Okay, hopefully you've had enough time to copy down. If not, I'll just sort of bring the relevant information into the writing pad, okay? So let's do this. I'll take this away. And let's get to the writing pad. Bam. And we're going to do this example. I'll bring in our tube. Bam. Such a nice tube. All right, to make this specific tube, they used a printing press. Get it? Because it was printed on paper? Okay. All right, so here we have a torque that's applied. That's 20 kilonewton meters. Our internal pressure on this guy, P internal, or what they call P here, is going to be 3 MPa. And I want to find sigma 1, sigma 2, sigma 6 on surface. And this is going to be our strategy. Okay, So the way that we're going to approach this is we're going to look at an element on the surface of this piece. Let's say an element, I'm going to draw it over here. This surface element here. Under what stress conditions is this surface element? Plane stress. Why is it in plane stress? Tell me. Did you just give him money under the table for his answer? Oh, okay. Gave him a low 5 over there. How do we know that a surface element here is in plane stress? Really? It's on the surface. If it's on the surface, it's in plane stress. Dang. You guys are killing me. I know you took 3005 with me. Dang. Come on. All right. So let's look at what a 2D element on the surface might actually look like. So the 2D surface element. Looks like this. And we're going to look at this in the original XY coordinate system. But I'm asked, what is the stress state in principal coordinates, principal material coordinates? So if I have these fibers that are sort of on this element that are running at this like 45-degree angle, which I was sort of told about in the problem, then I want the stress state not in the XY coordinate system. I want the stress state in the 1-2 coordinate system. So that might be a coordinate system that's aligned with these fibers generally, which is like the 1-2 coordinate system, right? I want it in principal material direction. That's the 1-2-3 axes. I could translate this to being here aligned with XY just for clarity's sake. It's the same sort of axis. And I'm told that the angle between the 1 and the 2 axes is 45 degrees. Okay. Given the torque on the object and the internal pressure, it's actually pretty hard to directly calculate what is sigma 1, sigma 2, sigma 6. It's actually like pretty difficult to do. So our strategy here is going to be, all right, so we got some internal pressure. It's going to provide us an axial stress and a hoop stress. Hopefully we remember our pressure vessel information. So here we have like a stress in the X direction. Here we have like a stress in the Y direction. And we're obviously going to produce a shear stress from our torque, which looks like this, which is going to be like tau xy. Okay. So we can easily find sigma x, sigma y, and tau xy. Then, if I want to determine what's the stress in the 1-2-3 coordinate system, how do I do that? Kev. Stress transformations. Good. To get me to like, I'll just draw this in matrix form. The stress in the 1-2-3 coordinate system equal to the transformation matrix T times the stresses that I have in this like XYZ coordinate system. Okay. Sort of what we talked about over the last couple of lectures. That's my general plan of attack for this problem. Rawr. Attack. Right, my man? Over the nose. Let's go. All right. So let's do that. Here we can calculate sigma x, which is steel. It's the axial stress for a thin-walled pressure vessel, which obviously you all remember. That means they don't remember. Is PR on 2T. Hopefully that equation like jives your memory a little bit. Yep. It rings the bells. All right, so if we're looking at a cylindrical thin-walled pressure vessel, let's remind ourselves what these particular variables are. So T obviously is the wall thickness. R is the distance to the inner radius for thin-walled pressure vessels. And so for us here, since the outer diameter is 200 millimeters and the inner diameter is 190 millimeters, that makes T what value, Austin? 5 millimeters, excellent. How many of you thought it was 10? Rawr! It is not 10. You have 2 T's. And that makes the value of R half of the inner diameter, which is 95 millimeters. All right. So my internal pressure I was given at the very start of the problem, it's 3 MPa. This value of little r, it's the internal radius. Here I'll do it in millimeters. It's 0.095 meters. Is that right? Yeah, that's right. Divided by 2 times my wall thickness, 0.005. Kind of ran out of space, but all right. Punch this in, you should get 28.5 MPa. All right. In the y direction, we have like the hoop stress, or what's, kind of like this sigma theta. It kind of goes by a couple of different variables, sigma theta or sigma hoop. Have a question? The equation here is PR on T, which obviously is just going to be twice the axial stress. So here that's just 57 MPa. And finally, if I want to calculate my torque, tau xy, how am I going to calculate the shear stress on this guy if I'm given a torque? What equation? Justin. Is it what? Say louder. No. How do I get a shear stress if I have an applied torque on a cylindrical member? Angle of twist not really applicable here. There's a direct calculation for shear stress given an applied torque. Yikes. TCNJ, thank you. All right. Okay. I made a boo-boo in the calculations that I have here, but okay, maybe I can have someone help me out. All right, the torque here that's applied is 20 kilonewton meters. The value of C is to the outside of the piece, so this is 0.1 meters. And J here, pi on 2 times the outer radius squared, so it's 0.1 meters squared, minus the inner radius squared. Sorry, not squared, to the fourth. Yikes. All right, Kev, you got your calculator? Can you hook me up? It's gonna be some big number. What is it? MPa? Okay, so we have 68.6 MPa. You agree with that? Going from kilonewton meters to megapascals, factor 1,000. Okay. So you agree with this? Okay. So there's our torque xy. Here's our sigma y, and here's our sigma x. So we can construct this stresses in the xy coordinate system. What do I got? Did some mental math. That's what I got. Yeah, okay. So here then we would have sigma x in sort of like this matrix form. With the following values. So sigma x, as we calculated, 28.5. Sigma y is 57. And then tau xy, 68.6. Here, MPa. How are we doing? We all cool with that? That's stuff you should have been able to do in like 3005. All right? It's combined like internal pressure plus torque on your piece, etc. gets you to this condition. This is stuff that should not be that hard to do. I'm just kind of like going through it because, you know, review. All right? But now here's where the composites comes in. But we want it in principal coordinates. So now we need our transformation matrix T. Okay? So that we can do that. Right? So we talked about a bunch of different transformation matrices. Which transformation matrix do I want here? What size? Right? This here is the plane stress transformation matrix. And that's because I'm in plane stress conditions. I have 3x1 vectors that I'm sort of trying to transfer between. Okay, so if we recall, sort of from last discussion, that transformation matrix T is not that crazy 6x6 that you saw before. And for 3 dimensions, we just have the 2-dimensional rotation matrix. M squared, N squared, 2mn. N squared, M squared, negative 2mn. Here we have negative mn, mn, and m squared minus n squared. That's your, yes, sir. Stiffness matrix. This is not a stiffness matrix. This is a transformation matrix. The factor of 2 floats because of the weird strain transformation stuff that happens. Yeah. Okay, so on we go with this. So our angle of theta is 45 degrees. Remember that we sort of had this before. That means m, which is cosine theta, will be root 2 on 2, I think it is. Yeah, root 2 on 2. N, which is sine theta. Same thing. Okay. So then if I input all of the values into the T matrix, I can get a transformation matrix that looks something like 0.5, 0.5, 1, 0.5, 0.5, negative 1, negative 0.5, 0.5, 0. Cool? All right, so finally, whoa. Whoa, baby. Might need your calculating expertise again here, Kev. Sigma 1, sigma 2, sigma 6. So these are the stresses and principal coordinates. This is going to be equal to my transformation matrix. Multiplied by my original stress vector that I had up there. I think it was 27.5, 50, 27.5, 28.5. 57, and I think it was 68.6. Yep. MPa. That calculation would give you the numbers, which are ooh, everyone's checking him. I didn't bring my calculatora today. Sorry. I could MATLAB it up real quick, but might not get it quick enough. Who's got it? It's a race. First value is? Okay. Are we verified? All right, we have agreement. Awesome. Thank you for checking my calculations in the chat. I appreciate that. You have agreement with the chat. Yes. All right. So there you go. I like this because it's, I think, relatively simplistic to understand what we're doing. You know, you got this tube, you're putting it in torsion, but it brings in like the composites where you might have to rearrange, you know, coordinate systems that you would traditionally work with, like your XY coordinate systems here, into a coordinate system that might be appropriate for material calculations. And we're going to show why it's important to be able to transformate. God, I just made that word up. We're going to show why it's important to transformate from stresses in the XYZ coordinate system to the 1, 2, 3 coordinate system when we go to failure. Because failure of composites is defined by stresses in the 1, 2, 6 coordinate system, not in any arbitrary coordinate system. So when you're talking about failure theories for composites, you need to transform from typically stresses that are in like an XYZ coordinate system to stresses in a 1, 2, 3 coordinate system. So you're going to have to be able to do this stuff. It's going to come up again, I promise you. Okay. So we get to see a little bit and bring it back to reality a bit. All right. Any questions on this example? Wanted to take a little time for it. No questions? No. Okay. Well, then let's talk about where we sort of were with this plane stress discussion. And I'm going to bring it back up in just the PowerPoint slides and we'll talk over it. So last time we were talking about transforming stresses to a 1, 2, 3 coordinate system using a plane stress transformation matrix with an XYZ stress state added. This is like what we just did with that example problem. Okay, where this is your transformation matrix here. You can also do the same for strains, where if you're going from an XYZ to a 1, 2, 3 coordinate system, it might look something like this, which is basically exactly what we just did on this problem. All right. So we also said that we could transform not just the stresses and strains, but you could transform your stiffness and compliance matrices using similar strategies that we did for the full 6x6 forms. Okay. Now, when we transform the stiffness and compliance matrices, we label them now not with like Q and S, but with Q bar and S bar. So here, this is just indicating that the bars over the top were not in principal coordinates. We're in some arbitrary coordinate system, like some X, Y, Z coordinate system. Same thing with the S. We're in some arbitrary X, Y, Z coordinate system, not the principal material coordinates, which would be like the 1 direction in the fibers, the 2 direction across the fibers, and the 3 direction on a plane. Okay, this is just some arbitrary coordinate system. But we know these transformation matrices can be written in terms of like sines and cosines and etc. So if you wanted to write each one of these individual elements, let's say Q bar or S bar, you could do the full multiplication for these T and T star matrices to get the full-blown glorious forms of each one of the individual entries, which you see here. Okay, because typically you're going to have stiffness matrix entries Q11, Q12, Q66, S11, S12, S66, S22, etc. You're going to have all those values in terms of material properties. So you have those. And if you're interested in like a stiffness matrix off axis, which would be like the entries here that you see here, or compliance matrix off axis, which is like the compliance matrix entries here, you could calculate them directly or use the stress transformation matrices that we showed before to get them. Okay. So why is this helpful? Well, we showed that this is helpful because maybe we don't want to look at stiffness in the one direction or two direction or the three direction. Maybe we want to talk about a stiffness in some arbitrary direction, the x direction, the y direction. Okay, maybe we want to talk about shear in an xy coordinate system because maybe that's the direction that we anticipate loading our structure. So I want to know if I make this composite material, how stiff am I if I sort of pull at this weird angle relative to the fibers? That just might be something that happens. Okay, just like you saw with that tube. Okay, you're pulling across the longitudinal axis of the tube. You want to know, okay, maybe how stiff is the tube in that like X direction? You might want to know that, okay? So we can do that by running these like mock experiments again, and then calculating like, okay, the modulus in the X direction, if we're just putting a stress in the X direction, we can do this transformation where we look at, all right, the modulus in the X is just a stress in the X on EX, epsilon X, but we know that the strain in the X follows this Hooke's law with this and so we can calculate that EX is 1 on S bar 1, 1. Or if we write S bar 1, 1 in terms of the principal material information, things like what we saw here, remember S bar 1, 1 is a combination of things that we get from the principal material compliance matrix, S11, S12, X66, S22. We can just remember that S11 is like 1 on E1, S12 is new 1, 2 on E1, S66 is 1 on G12, etc. And you can write a full-blown form of the stress or the modulus in the X direction in this sort of traditional way, where you have all of your material components there. If you know the rotation angle between the coordinate system of the material, so the 1, 2 coordinate system, and the coordinate system where you want to know the stiffness, let's say some X direction arbitrarily, then this is the equation that you want to use here. And it includes all of the angles and all of the material properties that you might know from, let's say, micromechanical models like Halp and Psi. Remember, if you have a unidirectional composite, you can calculate E1 using Halp and Psi with psi is infinity. You know this. You did this on your test. Some of you did it on your test. Some of you did not do it on your test and had a bad day. So there you go. You could do very similar things with a lot of other mock experiments to sort of show all of these things to be true as well. So if you want Poisson's ratio in the xy direction, here you go. You want the modulus in an arbitrary y direction, here you go. You want the shear matrix in some arbitrary xy coordinate system, here you go. These are all obtained from, let's say, just putting, in this case, you'd have just putting shear stress in the xy coordinate system and having like a mock experiment with just shear xy. And then you could calculate sort of what are the S entries required to do that and so on and so forth. Okay, so that's about where we left off last time, talking about how could we calculate engineering constants that are off axis given information about engineering properties that we know in principal coordinates. And this is the way that we do that, by leveraging what we know about the in material coordinate properties, as well as the angle between the coordinate system of the material and the coordinate system that you might be interested in testing across. All right, so that's about where we left off. So the last topic for this set of notes is looking a little bit more in depth at that full off-axis compliance matrix with engineering constants. So let's pick it up there. So we'll say transformed compliance matrix. in terms of well, let's not say transformed. Let's say off-axis engineering constants. And that's going to be kind of the topic for today. Okay, so let's again assume an applied stress only in x direction. That would be like a sigma x. So then the strains would be in this sort of off-axis coordinate system. We know to include like our now S bar matrix. Remember, this is 1, 6 because we contracted. And we're running like a mock tensile experiment in the x direction. Okay. And so we already sort of saw this and know that this is going to be something like S bar 1, 1 sigma x, S bar 1, 2 sigma x, and S bar 1, 6 sigma x. Those are going to be our strains in x, strain in y, and gamma xy. So from this, remember we saw that the modulus in the x direction, which we know is the stress in the x direction on the strain in the x direction, leads to the relationship that Ex is 1 on S bar 1, 1, or S bar 1, 1 is 1 on Ex. Okay, these are relationships that we sort of saw from this mock tensile experiment in the x direction. So we also know that we could define a Poisson's ratio, which is the ratio here. It's the ratio of the negative transverse strain to the longitudinal strain. This is your definition of Poisson's ratio. And this led us to something like nu xy is negative S bar 1, 2 sigma x over S bar 1, 1 sigma x. These guys cancel out. And we write S bar 1, 1 as Ex. And you could write nu xy. Actually, better we do this. You can write S bar 1, 2 is negative nu xy over Ex after a little bit of arrangement. Okay. So we have modulus in x. We have Poisson's ratio xy. I will introduce now a new parameter I promise you have not seen before. That is called the shear coupling coefficient. It is very similar to the Poisson's ratio, except it's not the relationship between transverse strain and longitudinal strain. It's the relationship between shear strain and longitudinal strain. Weird one. So new engineering constant. It's a bonanza. New engineer. How many times do you get a new engineering constant in your life? It happens like Rarely, okay? Like, you learn a lot when you're a sophomore, but when's the last time you learned a new engineering constant? Come on, when's the last time? Barely ever. How often does it happen? This is the first one we learned in this class. Come on. You got a new one, okay? This is the shear coupling coefficient. Okay, and it goes by the variable eta. We use eta a lot in this class. I don't know. Whenever they were doing composites, they just like ran out of variables. They're like, all right, that's eta. Okay, slap an eta on that guy. Okay. Alignment parameter, eta. Okay. Shear leg variable. Oh, okay, that's an eta. It's like, don't they know that other like Greek variables exist? Or for instance, if we have like eta and we have to put a subscript on here to denote which variables that we're talking about, we use xs. Here, this is the ratio of gamma xy, the shear strain that results, divided by the longitudinal strain in the x direction. If we go back up to our little mock experiment, we would see that this is S bar 16 sigma x over S bar 11 sigma x. These guys cancel. This is S bar 16 over S bar 11. But we know S bar 11 is 1 over EX as a reminder. So that means that this eta XS is equal to S bar 16 times EX. Or we have that the S bar 16 entry in terms of engineering constants, which I just taught you a new one, is this eta XS over the modulus in the X direction. Bam! So what is this shear coupling coefficient, and why have you not heard about it until now? That's what you're all asking, right? That's what you were asking. That's what you were asking. Why haven't I heard of this engineering constant before? Let me tell you. Take your normal isotropic material. And we'll load longitudinally. All right, we'll just like do this in two directions. So here's like your undeformed configuration. And then when we pull on it, it looks something like this, right? Pulling on it longitudinally, let's say with some sigma x, where we have our traditional coordinate system. Okay. We got some strain here that happens in the y direction. We agree. And that comes from what effect? Rhymes with shmoy shman. Okay, this comes from Poisson effect. right? We've all seen this in reality. Now, the shear coupling coefficient, remember by definition, is the ratio of the shear strain that we develop divided by the longitudinal strain that we develop. How much shear strain do you develop in an isotropic material when you only load it longitudinally? How much shear strain is developed in this deformed piece? Do we have any shear strain? No, there's no shear strain on that piece, okay? So for isotropic materials, this is equal to 0. That's why you never heard of it before, okay? You don't see a shear coupling coefficient for isotropic materials. You only see it for composite materials. And that's because if I like pull on something this way and the fibers aren't necessarily aligned with that direction, it's going to be stiffer in one way than it is in the other. So when I try to pull on it, it's going to want to try to resist me in one direction and not resist me in another direction. So it's going to want to be easier to deform one way than it is to deform in another. So let's put some picture to that. So for orthotropic materials, let's say loaded not in principal directions, you might want to consider this. You have an undeformed square again. But now let's put some fiber directionality to this because this is the composites class. So let's say you have some fibers that are running in here that generally are at this like 45-degree angle. Okay. Now when I pull on this, the stiffness in this direction is quite high. Okay. But the stiffness in like this direction is quite low. So if I pull on this in sort of a longitudinal fashion, it's going to want to move a lot in these general directions, but not a lot in these general directions because the stiffness is very high along the directions of those fibers. So what ends up happening is you still have this Poisson effect, which is present. It's still going to want to shrink in this general direction. But now you might get something that, I mean, I guess I could go either way, but you might get something that looks a little bit more like this. And I'm going to really exaggerate this. Yeah, that's right. I go the other way. No, that's right. Okay. And so just by pulling on this longitudinally, it's going to have this shear effect that happens. So here is not equal to 0. Okay? Because we've formed some angle here. Actually, the shear strain is here. This angle here is your gamma xy, right? So here we see shear strains occur. When loaded solely in tension. It doesn't happen with isotropic material. That's why you haven't seen this kind of idea before. So let's round out the S-bar matrix. with the other sort of engineering constants. You can have a similar idea where you just like floating only in this sigma y direction. You would find that S bar 1, 2 is equal to negative nu yx over EY. S bar 2, 2 is 1 over EY. S bar 2, 6 is now going to contain your shear coupling coefficient again, eta ys over EY, where eta ys is your relationship here, gamma xy now over the longitudinal strain in the y direction. Okay, then for loading only with shear. So this mock experiment, you'll have S bar 1, 6 is eta sx over gxy. S bar 2, 6 is eta sy divided by gxy. And you'll have S bar 6, 6, which is 1 on gxy. Or here, eta sx is epsilon x over gamma xy. I think that's right. Yeah. And eta sy is epsilon y over gamma xy. Okay. Last little bit that we'll say. We'll get you out of here. So you want to know this, you want to know this, you want to know this. So full form of S bar matrix in off-axis engineering constants is the following. One on EX, negative nu XY on EX, eta SX on GXY, negative nu YX on EY, 1 on EY, eta SY on GXY. And lastly, eta, oh, but that's a bad eta. Eta XS on EX, eta YS on EY, 1 on GXY. There's your full compliance matrix off-axis, written in terms of off-axis engineering constants. Yikes. All right, cool stuff. That'll be it for today. Homework 5 due on Thursday. Come see me if you got questions. Alex, email me about chess. I will destroy you. Right, 2, column 3, what is that numerator? This is eta sx.